Morning. Can you hear my voice?
Salam dokter.
Okay. So I think we can start lah kan. Walaupun macam ada lagi yang belum masuk. Okay, so for today we will continue for chapter 2, properties of fluid. So before we start, I think this Thursday we will not have a class, tutorial class, sebab I think di Bali kan. So we need to replace lah tutorial. However, I have uploaded the tutorial version in ITEL. So we proceed to our chapter 2, which is properties of fluid. So this is the continuous of the chapter 1. So for the chapter 1, we only you just introduce for the basic. So we go through to the properties of fluid in this chapter. So for the properties of fluid, you will learn the learning course outcome, which is the ability to distinguish different types of fluids, different basic properties, and apply theory and application of various fluid static properties, including measurement of pressure and solving hydrostatic pressure. So this is the where you're going to apply the calculation how to solve the problem. So there are only three outline for today lecture, which is first is density, specific volume, specific gravity, and specific weight. So you have learned in this week in chapter 1. So we're going to go through in specific for this subtopic for chapter 2. And then second is viscosity and compressibility. And final subtopic is surface tension and capillary effect. So for the density, specific volume, specific gravity, and specific weight, I think I shown this in our previous lecture, where for the solid mechanic, you're dealing with the rigid body. So in fluid mechanics, you'll see that fluid is not rigid and rate of deformation is significant in fluid mechanics. So this is the example of application of civil engineering for the application of fluid mechanics, such as the design water pipe networks, irrigation canals, hydropower capacity of a dam, design well, etc. So this is a few application of the fluid mechanics. So as you can see in Sabah, I think in KK we have the Bebagon Dam. So maybe we can have a site apa, visit to Bebagon Dam on the CEC program. So there are two type of properties because we're going to learn about the properties of fluid. There are two type properties, which is intensive properties and extensive. So for the intensive, it is regarding the mass in a system. For example, the temperature, pressure, and density. And then for the extensive properties, it value that depend on the size. For example, the total mass, total volume, and total momentum. So this is the uh, example of calculation. I think we have gone through this in our chapter 1, which is the basic one is to find the density, which is density is equals to mass over volume. So for example, density of plain water is 1000 kilogram per meter cube, while the mercury is having the highest high density, which is 13,570 kilogram per meter cube. So you can see from the high density to the low density, oil having the low density. So the homogeneous material have similar density regardless their size, shape, or mass. So we can see how to calculate the in one of the application calculation example of calculation to determine the mass of A in room dimension. The size of room is 4 meter times 5 times 3 at temperature of 20 degrees Celsius. So for the temperature for 20 degrees Celsius, the density is 1.204. The density equals to mass over volume. So we're going to find the mass of A. So we divide by the volume. So we get the mass is 72.24. And then we're going to find the weight, which is equals to mass times gravity. To get the answer is 708 and 67 Newton, or can also say it as 0.7 kilonewton. So you need, this is one of the example of direct question. So in your final or your test, it's going to be not direct question like this. So next is specific volume. Specific volume is defined as volume per unit mass. So as you can see, the formula here is specific volume is equals to volume of fluid we divide by the fluid of mass, or also equals to 1 over density. So different type of fluid have different type of specific gravity. So you can see this is the value for specific gravity. Just for example, for the water have the specific gravity of 1. So this is the table, different type of fluid. So what is specific gravity is defined as ratio of the density of the substance or fluid to the density of some substance at a specific temperature. So this is the example to find the specific gravity. Yeah, it's almost the same as you learn in chapter 1, right? So to find the specific gravity is density of fluid we divide by the density of water. The density of water is 1. So if specific of gravity of fluid is greater than 1, then the fluid has greater density than the density of water. And if the specific gravity is less than 1, the density of fluid is less than the density of water. So you can see, sudah tadi. Yeah, this one lah. So it is any density we divide to find the specific gravity. Yeah, we divide the density of fluid divide by the water. This one, which is 1. The next physical properties. And the next properties of fluid is the specific weight. So how to find the specific weight is weight of substance of fluid in Newton divided by the volume of fluid in cubic meter. So this is the formula. And the gravitational acceleration is 9.81. Okay, so you can use all this equation. Weight over volume, or weight is equals to ma acceleration. You take it as g because of the gravity over the volume, or density times gravity. So this is the next example. So we're going to find the density, specific volume, specific gravity, and mass of air in a room. Whose dimension, this is the size, 4 times 5 times 6 meter cube, with weight of 140 kg and at 25 degrees Celsius. So this is, yeah, we're going to find the air in a room. So our density is, yeah, we have to find all these properties, four properties. So for the density, mass over volume, we have the mass 140, and then the volume, given. So you get the density 1.167 kilogram per meter cube. And then specific volume equals to 1 over density. And you get 0.86. And for the specific gravity, the density of fluid over density of water. Density of water is 1000. So I get 0.00117. And then specific weight, the density times gravity, you get 11.45 Newton per meter cube. So this is the exercise one. I think I'm gonna finish early today because we have audit meeting audit. So I try to finish early. So you can try to do the exercise later when you on. So I'll skip that one, for the exercise. So you can try to do it. So next is viscosity and compressibility. So I think I've shown this in our last lecture in chapter 1 for the viscosity. So each fluid also have a different viscosity, and the temperature also will affecting the viscosity of fluids. So this is the definition of viscosity. It is a measure of resistance of fluid to the shear force. So there is a property that represents the internal resistance of fluid to motion, and that's also called as viscosity. And it's also the force that exerts on a body and in the flow direction of resistant force is called as drag force. This is the different type of fluid having different value of viscosity. So this is, for example, water having a low viscosity, and then to the medium viscosity, olive oil and honey having the high viscosity. So we usually use water or oil in the application of fluid mechanics. So next is dynamic viscosity. So dynamic viscosity can be determined when the force is measured as follows. So force equals to shear stress times with the area. Yeah. Why is times with the area? Because it related with the contact area. So as we can see, as water flow, the velocity in the middle is highest compared to the uh, water near the contact lah, yang dekat dengan wall. So kalau for example, you can see macam ni pipe. Ini bila air berjalan kan, di sini air mengalir, yang dekat bahagian terkena dengan surface tu dia akan jadi lebih slow. Tapi yang dekat tengah ni air dia lebih laju lah sebab dia ada contact. So that's why dia ada shear strength di sini, perubahan. Speed pun berbeza. Ya, so lah. Because we have the force ataupun contact area. So you can see this one, dynamic viscosity. Different type of fluid also having different value of dynamic viscosity. So this is one of the example of fluid with their value for the dynamic viscosity. So force required to move the upper plate at the constant speed, while the lower plate remain constant. So this one therefore you can write the equation. Force is equals to dynamic viscosity we times with the area. This one, volumes over L. So don't worry. I think we'll have the example of calculation for more understanding on how to find the dynamic viscosity or the force. So this is the example of temperature with the absolute viscosity. So as I mentioned earlier, the temperature will affect the viscosity. So as you can see, the highest temperature will have the will affect the viscosity, but it also depends on the type of fluid that's involved in the mechanism of the mechanic of the system. Hmm. So this is the example of a top. Yeah, dynamic viscosity of fluid between two cylinder. So this example, consider a fluid layer of thickness L, location between the surface of two cylinders. So this is the length to this one. Yeah, the distance between the two types of cylinder. So torque is equals to Fr, F2 force, and R is the radius of the inner cylinder. Then tangential velocity W is equals to angular velocity times with the radius. And the wet inner cylinder area equals to 2 pi R. So I get the formula is torque is equals to Fr. Fr force is inilah we just substitute the value F from the previous in this one. V over L. You just substitute V, this one, angular times radius, so times 2 pi R. So this is the final equation for fluid between two cylinder. So this is the first cylinder, and then this one is the second cylinder. Jadi our fluid jadi in the middle di sinilah. Yeah. So I think I'll provide the calculation juga. Jam double. Yeah. Next is kinematic viscosity. So kinematic viscosity is the dynamic viscosity of fluid divided by the density. In this one, dynamic divided by the density. So in general, viscosity depends on the temperature and pressure, but depending on pressure is weak for liquid compared to temperature, except for kinematic viscosity of the gases. So the density of gases is proportional to its pressure. And then the viscosity of liquid decrease as temperature increase. Maksudnya, for example, kalau suhu tinggi, viscosity dia decrease. So iron, macam for example, tu minyak lah, tu diesel, pump. Jadi bila dia panas, dia push jadi air makin laju mengalir. Kalau suhu menurun, for example, di cuaca yang apa? For example, in the temperature decrease, makin beku kan, the fluid become kurang. kurang viscosity. Jadi the movement is becoming slow, so it will affect the kinematic and also the dynamic viscosity juga lah at the same time. So this is the example to calculate the fluid between two cylinder. So the viscosity of fluid is to be measured using a viscometer constructed of two 40 centimeter long concentric cylinder. So the outer diameter of the inner cylinder is 12 centimeter, and the gap between two cylinder is 0.15. So inilah the length is 0.15. The inner cylinder rotated about 300 rotation per minute, and the torque is measured to be 1.8 Newton meter. So you need to find the viscosity of fluid for the experiment. So by using this formula, you need to determine the viscosity yang this one. Okay, so times the torque times length over 4 pi square. Inilah, yeah, this one. Because we want to find the viscosity. So our T is 1.8, torque. T is the torque, and then L is the length, the gap between two cylinders. So don't forget to change your unit to meter. So after change the unit, you get 0.0015 meter, and over 4 pi square r. Our radius is given. So that radius is 0.06 in this one lah, centimeter. Yeah, diameter dia, the outer diameter of the inner. So diameter, this is the diameter. So we want the radius. So that's why we divide by 2. Jadi 0.06 meter cube. And then NL. N2 dia punya angle, which is 300 RPM, rotation per minute. So you need to change minute to second lah. From the 300 rotation per minute to 300 rotation per second. So you need to change the value here. And then L, our length is 40 centimeter long concentric cylinder. So you need to change to meter, 0.4. The length here is 0.4. Don't forget to change your rotation per minute ni. The angular change to SI. So you get the answer 0.158 Newton second per meter square. Okay. And this example. So any questions so far? Still here? Okay. I'll proceed to example 2.4. We want to calculate the specific weight and kinematic viscosity. So given information on the density and dynamic viscosity of mercury, so this is the density and then the dynamic viscosity. So this is the given information. We need to calculate the specific weight, which is specific weight density times gravity, and density is given times with gravity. Then for the dynamic viscosity is equals to find the kinematic viscosity equals to dynamic viscosity over density. So this is also given. So I think this is a straightforward question. Get the answer So 133 kilonewton per meter cube for specific weight, and for the kinematic viscosity is 1.15 exponent negative 7 meter cube per second. And this is the example exercise 3. You can try to do it later. And you can try to ask me if you have any question. You can try to do it later for the exercise 1, 2, and exercise 3. So next is coefficient of compression. So this is when we apply a force for the compressibility. So as we know, the volume of fluid change with a change in temperature or pressure, but different fluids have different rate of volume changes. So therefore, to define the properties, you can measure the coefficient of compressibility or book models of elasticity of the fluid. So this is the sample of coefficient of compressibility. When you apply force, there will be a change in volume. Yeah, example there. The fluid will become compressed. So when we apply more pressure, fluid will be compressed and release the pressure. So the fluid will expand it as similar with solid. So therefore, Young modulus of elasticity can be applied for a fluid. So okay, this is the Young modulus of elasticity. So V1 is the initial volume before the pressure is applied. Then P is the change in temperature, which is force over area, and then you divide with change in volume. So one how to collect the compressibility. So I think I have provided the tutorial question, so you can try to do it. To do the tutorial on how to apply the calculation, and you also can refer the equation. So we will not have our tutorial class this week, and we will discuss it next week for the tutorial 1 and tutorial 2. The answer for tutorial 1 and tutorial 2. So next, I think this is the last subtopic, which is surface tension and capillary effect. So what is surface tension? It's surface tensions generate observable phenomenon. So the surface molecules are pulled inward. And this is, as you can see, the water molecules. And the molecules are pulled in all direction. So you can see an example of surface tension. I'll show you in the next video. Like
You took a glass of water and a needle, and you took that needle and you very carefully dropped it on the water, it would stay there. And it's not because it's floating. This needle would not be floating on the water. This needle is more dense than water. And we know that if it's more dense, then it should sink. So it's not floating. It's actually just sitting on the surface because there's surface tension. Water is a liquid that's capable of having a significant amount of surface tension. And you know it's surface tension because if you were to come in here and exert a little force down, breaking the surface tension or pushing this needle just below the surface, then it would sink. It would sink like a stone and just drop immediately to the bottom of the cup. So why does water have this property of surface tension? It has to do with the fact that the water molecules within this liquid are attracted to each other. This water molecule can form hydrogen bonds with the other water molecules around it, and it gets pulled toward them. And there's a term for this. We call this cohesion. So the fact that water molecules and other liquid molecules are attracted to each other is called cohesion. But what does this have to do with surface tension? Well, the key is these water molecules would like to bunch together. They want to group together if they can. So what would this water molecule do I mean, which way is he going to go? How does he pick which one to group with? That's a problem. Here in the bulk of the liquid, he can't decide. Or in other words, let's just say got pulled toward this molecule. Well, it's also getting pulled to the left by all of this. By this one's pulling it back to its original position. This one's pulling it back to its original position because there will be a component of that force that'll point in the direction of its original position, as well as this one to the left. So these are restricted. These molecules here in the bulk of the liquid have too many other water molecules around them dictating where they need to be, because if they tried to get displaced, it'd pull them back to that position. However, at the surface, there's no water molecules above them. These are freer, they're less restricted. So that allows these water molecules on the surface to group together a little better, form stronger, tighter bonds, closer spacing at the surface in such a way that they form a tension that's not present in the bulk of the liquid. Yes, these water molecules down below will prevent them from just grouping into one big clump in the center, but since they're less restricted, they can form these tighter bonds here at the surface, and this allows it to support a pressure from above. So this allows it to support a certain amount of weight, which allows the needle to rest on the surface. A few practical applications of this, one clinical: if there's a bile present in urine, you could detect its presence because it lowers the surface tension of urine. So it gives you a test of whether the liver is metabolizing things the way it should. Another application is if you go camping and you're in the tent, it's raining, and the tent gets raindrops on it. Most tents will keep the water from seeping through, but you're going to be tempted. You're going to be sitting in here, you're going to be like, that looks cool, and you're going to touch it, but you're not supposed to touch it, because as soon as you touch it, you may break the surface tension. And once you break the surface tension, that water is dripping into your tent from that spot that you touched it, and you're probably not going to have a good night. So resist the urge to break the surface tension on your tent if it's raining out. And when you wash your hands, when we use detergents, if you washed your hands with just regular water and that's it, sometimes the surface tension's too great. These water molecules are too bound to each other. They form too big of a clump. It doesn't look like it. It looks perfectly smooth. But on a microscopic level, the water's not.
So yeah, so the surface tension, for example, tadi lah, if I can say it in a simple way, for example, macam kalau bagi makan ikan di aquarium, bagi makan ikan, mula-mula tu makanan terapung, and then bila kita sentuh ataupun ikan tu yang pegang, baru ada force, baru tu makanan terjatuh kan. So this is because of the surface tension. So itu one of the example, was the simple example. So for the surface tension, ini the interfacial liquid at the boundary between a liquid and gas, we have like a membrane that possesses tensile strength. So the tension is measured as force acting across a unit length. So the surface tension for liquids, again, liquids are called as interfacial tension. So as you can see, this is the figures. You have the surface tension and the gravitational force. So liquid of non-wettable surface tension dominating attractive force on the surface. And then this one is an example of surface attractive force. When the attractive force to surface exceeds the surface tension, the liquids wets the surface. So this is the equation or formula where we can express the surface tension. So surface tension is equals to force over 2B. B itu di surface lah. So it's also related with the temperature for a given substance. So different type of fluid also having a different value for the surface tension. So this is the example for the surface tension of some fluid in A at 1 atm and 20 degrees Celsius. So this is the same explanation as in the video. For example, the soap and detergent. So this helps in cleaning process of clothes by lowering the surface tension of water so that it's more readily soaks into pores and soil area. So this is the one of the example, one of the application. Next is capillary effect. Capillary effect ni this one lah. This depends on the uh, type of fluid. For example, the capillary effect of water in this one lah. And for the mercury in this one. So the capillary effect ini lah. I think so capillary effect is also can define as rise or fall of liquid in small diameter of tube due to surface tension. And then the curved free surface of liquid in a capillary tube is called as meniscus. Inilah because that we call as meniscus. Untuk water dia the shape dia U, and for mercury ia terbalik. The strength of the capillary effect is quantified by the contact angle. This is the angle that the tangent to the liquid surface make with the solid surface at the point of contact. So there ada dua example, which is the capillary effect for water and mercury. Ini dia punya contact angle. Contact angle for water is less than 90 degree. This one lah. And then however for the mercury, so dia punya surface, the shape is U terbalik. Gini, macam set punya sign. The contact angle is more than 90 degree. So back to do with water, atmospheric A, the contact angle of water and glass is almost 0 degree. So that is the reason why meniscus of water is in full condition. Yeah, untuk smiley. Untuk U or smiley. So for water, the contact angle is 130 degree in mercury or glass. So capillary effect can be explained by considering the cohesive force and adhesive force. So for cohesive forces is the forces between many molecules, and adhesive force is forces between unlikely molecules such as water and glass. So ni meniscus, if the shape macam ni this one smiley or U, then you can know that the type of fluid is water. Contoh kalau yang tadi shape set meniscus. So usually the height is more than 0. Sini ada value. It's different with the mercury because the opposite situation occurs in mercury and glass, which cause the liquid surface near the glass wall to be suppressed. Maksudnya ini kita punya bekas lah, your container. So this we put the meniscus, we put the sini cylinder, and then our meniscus, kita punya liquid will be lower than the height of the container lah, which is the height will be less than 0. So as you can see, ini the meniscus shape is set, U terbalik, so it is easy to identify this mercury. Force balance can describe magnitude of capillary rise. Capillary rise ni yang this one lah. So weight equals to mass times gravity. So it's also equals to density times volume times gravity. So kita punya PGV, volume for meniscus ialah pi r square h. Kenapa ada pi? Because kita punya this is the shape of the cylinder. Cylinder tu bulat kan. Jadi pi r square dia punya radius of the cylinder, and then the height tu yang ni lah, tinggi tu ayat. Then equating the vertical components of the surface tension to the weight give yang ni untuk force balance. W equals to F. So W, this is the equation, and then force 2 pi r, ini the angle in force tu yang from the previous subtopic tadi. So you can determine or can calculate on how to find dia punya rise ni. This one lah, this is the formula. Ini this is the contact angle. Only over density times gravity times r. We see the video steps.
In a recent video about water transport in trees, we described a phenomenon called capillary action. As the size of the capillary tube decreases, the higher the liquid rises in the tube. With a wide tube, like the size of a test tube, the rise is negligible. But why is this? What are the forces at work? That's what we want to look at today. Let's break it down into its parts. First, there is an upward force caused by adhesion between the liquid, let's say water, and the sides of the glass tube. Adhesion comes about because of the interaction between the water molecules and the silica in the glass, which creates an attractive force pulling the water up the sides of the wall. Adhesion creates a meniscus at the sides of the glass tube. There is also the downward force of water in the column due to gravity. The downward force equals the mass of the water column times the gravitational constant. The mass of the water will be the volume times the density, given by the Greek letter rho. The volume of a column is pi r squared times the height, h, so the overall downward force will be pi r squared times h times rho times g. The upward force has to be proportional to the circumference of the circle at the meniscus, 2 pi r, times some adhesive force constant, let's call it A for now, which represents the attraction between the liquid molecules and the material of the tube. At equilibrium, these two forces are equal. Right away, we see something interesting. Both the upward and downward forces increase with increasing radius of the tube. But as the tube gets bigger, the downward force increases with the square of r, whereas the upward force increases as r to the first power. So as the tube gets bigger, the weight of the water in the column exceeds the upward force. If we solve for the height, we get h equals 2a over rho gr. We've derived an equation that you won't find in a textbook, but it does resemble a well-established equation known as Jurin's law. Jurin's law states that the height of a liquid in a capillary tube is inversely proportional to the radius of the tube. Here, our adhesive constant A is expressed as measurable quantities. Gamma, the surface tension of the liquid, which is a constant for a given liquid at a given temperature, and represents the cohesive forces between the liquid molecules. The other factor is cosine theta. Theta is the contact angle that the meniscus forms along the side of the tube. The contact angle depends on the liquid and the tube material, for example, water and glass. As the adhesion of the liquid to the tube increases, the angle theta gets smaller and cosine theta approaches 1. If the adhesion of the liquid were very low, the angle theta approaches 90 degrees and cosine theta approaches 0. Jurin's law has been validated in hundreds of experiments and forms a cornerstone of hydrodynamics and microfluidics, the study of the behavior of fluids at small scale. Jurin's law is not limited to water. It can be observed in other liquids too, even mercury. When a glass tube is placed in mercury, the meniscus is actually below the level in the reservoir. This comes about because mercury has no adhesion to the glass. The meniscus is convex instead of concave like with water. Mercury has high cohesion, that is, the mercury atoms interact strongly with each other, creating high surface tension. With theta now greater than 90 degrees, cosine theta is negative, making height h a negative value also. We hope this video has provided some insight into the factors that go into capillary action. Thanks for watching, and please subscribe to Science Sketch.
I have the next video.
Have you seen a paper towel soaking up water which was spilled? Do you know how this happens? The paper towel has narrow pores which absorb water by capillary action. Do you know how this happens? Water by capillary action. To understand capillary flowing activity, for this we need two capillary tubes of different diameters and a beaker of water. Take a half-filled beaker with colored water. We will use colored water here so that we can clearly see the water levels. Place the capillary tubes in the beaker vertically. See the water levels. The level of water in the capillary tubes is higher than the level of water in the beaker. The narrower the capillary tube, higher the water level. Why does this happen? All liquids have cohesive properties because of which all the molecules tend to stay together. This creates surface tension. Some liquids have adhesive tendencies by which they are attracted to substances unlike themselves. For example, water adheres to glass. Thus, in the experiment, as the water along the edges of the glass tube adheres to the glass, it rises along the sides, forming a small curve of water. The remaining water in the middle of the tube too rises up as a whole because of surface tension, which holds the water molecules together. These two phenomena together raise the level of water in the glass tube. The level to which the liquid rises is dependent on the diameter of the capillary tube. Capillary action is used in many modern fabrics to remove sweat from the surface of the skin. Did you know that water rises up the stem in trees by capillary action?
So next, so the video, as you can see, when we're having the small size, small diameter, the height of the tube will be increased compared to the wider or bigger size of capillary tube. So the next is capillary action. Capillary action is when the water is sucked into a tube because of the combination of adhesion and surface tension. So the surface tension makes the water rise into the tube, while adhesion makes the water sticks to the sides, and cohesion brings the other molecules with it. So the smaller diameter of tube, the higher water will be rise due to the surface tension. So this is the same one as the video explained just now. So this is the equation where the magnitude of capillary rise H in a circular tube can be determined from a force balance of the cylindrical liquid, column of height, edge in the tube. So this is the height. So if you see the meniscus shape is this, so we can simply know that the liquid is water. So the equation is the equation. The capillary rise is inversely proportional to the radius of the tube and density of the liquid. So there are three of capillary action. So when the bottom of liquid column is same level as free surface of the tank or reservoir, thus the pressure they equal to the atmospheric pressure. Second is when the angular contact is less than 90, the edge is positive, which means has a rise. So you can simply know that this is a water. And then for mercury, the angular is more than 90. So it will be negative because the height of the liquid in the cylindrical tube is lower. The capillary rise is inversely proportional to the radius of tube. So the thinner the tube, the greater the rise or fall of the liquid in the tube. Next is capillary action and effect. So in the practice, the capillary effect of water is usually negligible in tube whose diameter is greater than 1 centimeter. So therefore, pressure measurement using manometer and barometer must use large tube, which is more than 1 centimeter to minimize the capillary effect. So this is the example or the application of the capillary effect. So I think you will see this in your lab in year 3. Next is capillary also rise or fall depending on the density of liquid. So lighter liquids experience greater capillary rises. I think that's all for today lecture. So you can continue can try to do the exercise, which is exercise 1. We have 3 exercises. You can try to do it later. Exercise 1, exercise 2, and exercise 3. Also, I have uploaded the tutorial question. Yeah, this one. You can try to do it and submit the tutorial on Sunday. Yeah. So we'll discuss the tutorial. I think cannot view. We will discuss the tutorial 1 and tutorial 2 next week. So as I mentioned, there is no tutorial for this Thursday as we're having the Babali holiday. So I think that's all for today. So most of the attendance. I think there are 58 of you. And some of you haven't scanned for the attendance. Yeah. So you can, for those who haven't scanned, please scan for the attendance. Okay. 58. I think that's all for today lecture. Happy holiday, everyone. And happy Deepavali for those that celebrate Deepavali. So sorry, I have to finish early for today because we're having an audit meeting at 9. Yeah, starts about this start. So that's all for today. Thank you. Don't forget to submit the tutorial.
Thank you, Dokter.
Thank you, dokter.
Thank you, dokter.
Thank you, dokter.